In this video, I wanted to look at a rational function where the degree of the numerator was actually larger than the denominator and talk about, again, all the same sorts of things. And going back over the guidelines for that specific case, in the case that the degree of the numerator polynomial is larger than the degree of the denominator polynomial, it says that there is no horizontal asymptote. It says instead there will be what we call a slant asymptote, whose equation is given by the quotient after performing long division of p over q. And so if you're like, what the heck are you talking about? What do you mean? Let's look at c of x and kind of dive into it. And let's actually start with the graph this time, which is always the easiest, fastest way to try to understand the behavior of any function. But of course, our goal here is to understand why and learn how we can find these things by looking into the algebra. But if I graph this polynomial, or sorry, this rational function, which is a ratio of two polynomials, what I get is, again, another graph that is very strange and very different if you're not prepared for, these different sorts of behaviors that are common. But notice one of the things that was common about a lot of the other examples is that as you head towards infinity, it sort of is flattening out. It's heading towards 0 or heading towards 1/2 or heading towards wherever there was a horizontal asymptote in each of those cases. But this one is notably different because as we're going to the right, notice that it's actually not flattening out. It's actually leveling off into a straight line. And if you kind of imagine in between this graph, there's what we refer to as a slant asymptote in here, which is because it's not a horizontal asymptote, it's actually going at a particular slant. So I wanted to mention, how do we find the equation of that? How do we, and why, and all of those sorts of things. But let's do the same sort of procedure we were doing by starting, let's find the vertical asymptote, the horizontal asymptote, and all the intercepts in that order, again, by practicing using the guidelines. And as I kind of wrap up this week's lecture, this is one of the approaches that you can use with a rational function. If you're trying to figure out all of the traits, you can kind of do them in the same order to sort of, if you're the type of person who likes to kind of do the same thing and you're really good at building up habits and patterns, it's kind of good to do things in a particular order. But anyways, let's start with the vertical asymptotes. They're always done by setting the denominator equal to 0. Here the denominator is only, it's degree 1, so there's only one 0, right? X is equal to 3. And there's only going to be one vertical asymptote. And as we can see from our graph, that appears to be consistent, right? Because they're at, right there at +3, you can see that there's that break or gap, which is indicative of a vertical asymptote. And let's just create a little sketch here on our paper as well. And I'll continue to use colors for my asymptotes, but this one's going to occur at x equal to +3. And again, that would correspond to a gap in the domain and an undefined value in the function, no matter what. So the horizontal asymptote, this is where it's different than the other examples, because when the denominator was larger degree, the horizontal asymptote was always at 0. When they were equal degree, the horizontal asymptote was at a ratio. But when the degree on top is bigger, you're not going to have a horizontal asymptote. That's always going to happen. So this is another little fact you can remember, which again, if you're wondering, should I memorize all of this stuff? It's really not that important to memorize all these things, but these are helpful traits to understand about rational function. And when you're in calculus and you're trying to find the limits of these things, it's a very handy way to check yourself to see, is this working the way I think it should? Of course, you can always go back to the graph and look at it, but I'm just trying to train you what to look for. And also, if you want to just rely on your brain, how you would do that. But in this case, the degree of the numerator is bigger, and that's something that's important. Degree of p is greater than the degree of q, which implies that it has no horizontal asymptote, nor no horizontal asymptote. But instead, it will have a different type of asymptote, which is sometimes called an oblique or a slant asymptote. And again, as I was saying earlier, it's basically a slanted line that's outlining the pattern instead of a horizontal line that's modeling what's happening at the end behavior. And so the next question is, how do we find it? But basically, if you just divide it, and also this is something that when we have a larger degree on top, we could always just divide these polynomials, and what we'll get is a quotient and a remainder. And basically the quotient is the slant asymptote. So let's go ahead and do that. Now we could divide these polynomials synthetically because our denominator is degree 1. So let's do that. So I could take x squared minus 4x minus 5 and divide by x minus 3. Drop, multiply, add, multiply, add a negative 8. And we wouldn't necessarily expect them to be divisible. So remember, we only want 0 when we're trying to factor it. In general, the remainder doesn't have to be 0, but the last number over here is always the remainder, and this part right here is the quotient, which is our polynomial. And basically the equation y is equal to x minus 1, this is going to be the equation of the slant asymptote. And notice that equation, it's actually just a linear equation, right? Y equal mx plus b. It has a slope of 1 and a y-intercept of minus 1. And basically, if you're there's going to be a horizontal, or not a horizontal, a slanted line, which is the asymptote. That's exactly what this is. It's a line. It's the equation of a line. And actually, if you graph your slant asymptote next to your rational function on the same grid, let me go ahead and do that just so you can kind of see what the slant asymptote looks like. What I have is an equation that fits right in the middle, kind of like how that that horizontal asymptote fit right in between the gap of those other cases when the denominator had an equal or larger degree. But anyways, again, when the numerator has a larger degree, you're always going to get a different type of asymptote. It's not going to be horizontal, it'll be a different type of curve. In this case, and you can always find it by just doing straight division of the polynomials. And anyways, like if we wanted to graph this, graphing the slant asymptote would be very helpful in trying to recreate a sketch of it. And again, that had a slope of 1, so a 45-degree line, and a intercept of minus 1. So that's kind of where I'm getting this. And that's the equation y is equal to x minus 1, which is that slant asymptote. And otherwise, once we have all that, the graph will kind of fit in between the asymptotes. They're just a little bit different. And also, we could find the intercepts. So in this case, the y-intercept is going to be at negative 5 over negative 3. So positive 5/3, again, because that's always found by plugging in 0. And the x-intercept is always going to occur based on the numerator being set to 0. So if I set x squared minus 4x minus 5 equal to 0, this one I don't need in the quadratic formula because I think I can factor it without much trouble. That should be x minus 5 times x plus 1. Let me double check. Yeah, that makes sense because those two multiply to be negative 5 and they add to make negative 4. That all checks out. And so notice that we should have two x-intercepts, x equal 5 and x equal negative 1 as our x-intercepts. Because the x-intercepts occur when the top is 0, the vertical asymptotes occur when the bottom is 0. And so to sort of summarize, it's important to know, well, what happens when I set the top equals 0 or bottom equals 0, because it does something different in any case. So what I recommend is just practicing this. Use the guidelines to work on your homework problems for this section and see if it helps you figure it out. And I think it just takes practice and some repetition. And hopefully all of these different tips, I know it's been a little bit disorganized, but all of these different strategies can help you find the various traits of a rational function. And so let's go ahead and graph the x-intercepts. I had 5 and negative 1, which should have also been x-intercepts, and the y-intercept occurred at 5/3. And if I go ahead and connect the dots, I can see that the graph of the function itself was above the slant asymptote on the left-hand side, and again kind of exploding upwards towards that vertical line. And over here it's kind of working like this and fitting in between it in that way. But again, even different. And the more and more vertical asymptotes and higher the degree of the numerator, you could your slant asymptote could look like all sorts of different things. And again, just to sort of reiterate, the quotient will give you that slanted asymptote. And actually, I wanted to talk about, well, why? In this case, why does having a larger degree do this? But really, the essence of this is because if I actually, when the degree of the denominator is larger, I could actually compute this division, and I did, and I could write that as, well, that's x minus 1 plus the remainder divided by the original divisor. And basically, if I actually just calculate the division of those two polynomials, I would actually get this sort of answer, which is a different way of looking at it. But if I look at it this way, I could kind of look at this as a polynomial plus another simpler rational function, where the polynomial is the line x minus 1, which gives us our trending outlining behavior, the line in blue, which outlines the end behavior, which is kind of the purpose of the slant asymptote. Whereas the remainder over the quotient is still a rational function. We still have this vertical asymptote at 3. So I kind of imagine it as, well, we have this function, which is just a line like this, but we're chopping it right at 3, and that's what causes this weird gap and break in the curve, because it wasn't divisible. And when it is divisible, what will happen is that asymptote just won't even happen, and you'll have instead what we call a hole. But anyways, that's going to wrap up this chapter. We've gotten really deep into rational functions and all the different traits, more than enough to progress at this point in time. There's a few other examples if you'd like to challenge yourself to continue to look a bit further, and a few more on the last page. So, obviously work on your homework first, but if you want to keep trying some other ones, and if you're having trouble with anything, we still have 2 weeks before the next exam, so there should be plenty of time. But this is a difficult chapter because there's so many different traits and so many things to look for. And the graphs of these functions are just plain weird. But again, hopefully these guidelines help you to find these things in an algebraic way so you can solve the location of these asymptotes a little bit easier.